Okay, so we're still looking at some of the common sketches. So in the previous video, we we looked at horizontal. So we've looked at horizontal. Then here we can now move on to look at oblique projectile motion. So under oblique projectile motion, you have a number of sketches that you need to know. So the most common sketch under oblique projectile motion is this sketch here, where you're given a ball projected from the ground, and it forms a parabola to end at a certain point here in the same level. So this is one of the common sketches under oblique projectile motion. So under this sketch, the things that they'll ask you to find, number one is they might ask you to find the maximum height of this projectile. They might ask you to find the horizontal range. They might also ask you to calculate the time of flight. So we said for this type of setup, there are specific formulas that you need to know. Okay, and the formulas for this type of shape, they were derived from these general ones, the ones we got in the first video under projectile motion. And what were these equations? Number one equation was we looked at the time taken to reach the maximum height, which was given by VO sine theta divided by G. If you attended class, you know where this is coming from. The other equation was the total time of flight was given by 2VO sine theta divided by G. And the other equation I'm supposed to know under this sketch is for the maximum height, which is given by VO squared sine squared theta divided by 2G. Then the other equation is for the horizontal range, which is given by VO squared sine 2 theta divided by G. So these are the equations that we looked at under this type of a setup. Okay, so whenever they ask you for the time of range, these are the formulas that you're supposed to know. Time of flight, the time taken to reach maximum height, how to calculate the maximum height, how to calculate the horizontal range. Then how to calculate the final velocity in the x and the final velocity in the y. We still go back to our formulas which are here. The final velocity in the x will be given by this one, the final velocity in the y is going to be given by this one. The only difference is that here now the object is moving up, so it's going to be opposing gravity. You're going to have negative g. So 1, 2 plus 1, 2, 3, 4. These are the formulas that you're supposed to know under this sketch. Remember to say these formulas are only applicable if a shape looks like this. If it's not like this, you cannot apply these formulas. Okay, you should always remember that. And then the other common sketch that you come across under projectile motion, oblique, is where it has been projected, an object has been projected from a certain height, then it goes upwards up to the ground. Okay, so the only mistake that I've seen is that most people confuse these two sketches. Please, this is horizontal, this is not horizontal. So I don't expect you to apply these simplified formulas when you get a sketch like this. This is under oblique, okay? And for this one here, there are no specific formulas. The only formulas that you can get from the previous sketch, this one here, is the time taken to reach the maximum height and the formula for the maximum height. These are the two formulas from this sketch which are applicable to this sketch. So you're saying they might ask you to find the maximum height. So even in this sketch, for you to find the maximum height, you can just say VO squared sine squared theta divided by 2G. And the time taken to reach maximum height is VO sine theta over G. These are the only formulas from this sketch that can be applied to this one. Okay, not when they ask you to calculate the time of flight for this sketch here and you use this formula which is here. The rest of these, this one and this one, are only applicable to this shape which is given here. So we are only getting two equations. The equation that is the time taken to reach maximum height and the maximum height. Those are the two equations that we can also use on this sketch. Then the other thing that you should know about this sketch is that the ball is moving up, so the acceleration in the y is going to be negative g, since it is opposing gravity. And then this h here, the h is supposed to be negative also. So whenever you're given the h, so when you're calculating, this h here is supposed to be negative. Where is the negative coming from? We know that change in y is going to be given by y minus y. So the final minus the initial, meaning the change in y is going to be, what will be your final? Your final is a ground, so it will be 0 minus h. So the change in y is going to be negative h. That's why I'm saying the h is going to be negative, and the acceleration in the y is going to be negative g. And then for other things, such as the velocity, the initial velocity in the x, the initial velocity in the y, we'll still stick with these formulas which are here. The final velocity, this one, we apply this. So these equations are the ones that we're going to be applying for this sketch. And then we've just taken two equations from the one that was forming a parabola, this one. The time taken to reach maximum height and the maximum height can be applied to this sketch, which is also here. Then the last one is the other sketch that you can come across, and oblique is where it has been projected from the ground to a certain height h. Okay, so for this one also you can apply the formula for maximum height to calculate the maximum height over 2g. You can also use the time taken to reach maximum height sine theta over g. Okay, but we are not saying this h is also this h. No, when they ask you the maximum height for this sketch, you can use this formula, and the time taken to reach that maximum height, you can also use that formula. Then for other calculations, remember your general formulas. Okay, so a summary of what we've done. Number one is you have a sketch like this where you have a parabola. You have specific formulas that you can use here: the time of flight, the range, the maximum height, and the time taken to reach maximum height. Then the other type of sketch is this one, where a ball has been projected from a certain height. So you said the formula that you can use is, you can use the one for maximum height to calculate the maximum height. You can use the time taken to reach maximum height. And the other things is the acceleration is going to be negative and the height is also going to be negative. Then for other calculations, these are the formulas, the general formulas. You go back to the general formulas. But if they ask you to calculate the maximum height, you can use this formula. If they ask you to calculate the time taken to reach maximum height, you can also use this formula. Other things you calculate using the general formulas which are here. And the last one is this one here. For all other calculations, use your general ones, but for a maximum height and the t, you can use these two equations which are there. Okay, so let's look at an example and oblique projectile motion. Okay, so let's consider this as an example. They're saying a projectile is shot at the air from the edge of the building top, which is 125 meters above the ground level, with an initial velocity of 65 meters per second at an angle of 37 with horizontal as shown. So this shape here is similar to this one. So a sketch has been provided. Okay, so we said whenever you're given a sketch like this, the only two formulas that you can get from this parabola here are the time taken to reach maximum height and the formula for the maximum height. Whenever they ask you to calculate the time of flight, you cannot use this one, and whenever you're calculating the range, you can also not use this formula which is here. So when they ask for the time of flight, the horizontal range, the formulas that you are going to use are these ones which are here. So let's get back to our question. They are saying a projectile has been shot from the edge of a building, and this is the setup that has been given. So the first one is I want you to determine the time of flight. So how do you calculate the time of flight? We said you go back to the formulas here. So you check what have you been given. You have the height, you also have the initial velocity. So from the general formulas which are here, which formula can help us to calculate the time of flight if you've been given the height, which is the distance traveled in the y? So the only formula that can help us is this one here. So this is the formula to use to determine the time of flight. So the formula is y is equals to VO sine theta multiplied by t. Then when you look at the general formula, it's saying plus or minus, so just get one. Since the motion of this object is moving upwards, it simply means you'll get negative. So you say minus 1 over 2 gt squared. Okay, so the only mistake people make is when you hear time of flight, or then you go back to this shape, which is, oh, there is a formula for time of flight. No, this formula is only applicable to a shape like this. If you have a shape like this, you go back to the general formulas from the equations that we are using in the first video. So we use this equation which is here, and this is what we have. The only difference is that plus or minus, you choose one. This is a negative that we have 1 over 2 gt squared. Then you can now start replacing in. You already have the value of the y. The y is the height of the building, which is 125. So when you start replacing in, remember when you look at this sketch, we said the value of this h here is supposed to be negative. Okay, so therefore you say your y is going to be negative 125 is equals to, what was the initial velocity? The initial velocity was 65. So this is going to be 65 sine 37, and the time is t minus 1 over 2. Gravity is 9.8, and then the time of flight, this is t squared. So you're going to have negative 125 is equals to, so you can punch that on your calculator, 65 sine 37. So 65 sine 37, you are going to get 39.1 t minus 4.9 t squared. And then at this point we can just rearrange this so that we form a quadratic, because the quadratic is supposed to be in the form of x squared plus bx plus c, which is equals to 0. Okay, so I can get the negative 4.9 on the other side, so this will be positive 4.9 t squared. You can take this on the other side, minus 39.1 t minus 125 is equals to 0. Okay, so meaning the value of the a is 4.9, the value of the b is negative 39.1, and the value of the c is going to be negative 125. Okay, so to calculate the t, you say time is given by negative b plus or minus the square root of b squared minus 4ac over 2a. So you're replacing the value of a, b, and c. So you're going to get your time 1. You're also going to get your time 2. I think when you place in your calculation, this was given 10.4, and this was given maybe 2 point something. So you discard the negative time and focus on the positive, which is 10.4. So that is how you determine the time of flight. Okay, and then how do you calculate the range? So how do you calculate the range? The range, we said it's distance traveled in the x-axis. So you go back to this formula which is here, this one, distance traveled in the x. So to calculate the range, you say the range is equals to VO cos theta multiplied by the time of flight. The only mistake is they ask you to calculate the time, the range, then you go back to this one here. You get to say, oh, we have a formula for range. No, this one is only applicable to this one. For all other calculations, you go back to the gen one. So range is distance, that's why I've gotten this equation which is here. So you say your range is going to be, the initial velocity was 65 cos 37 multiplied by the time of flight. The time of flight is what we are from determining your 10.4. So you can now say your range is going to be equals to 65 cos 37 multiplied by 10.4. So you're going to get this is 540. You can just get 540 meters. And then the last one is the magnitude and direction of the final velocity. So we want the magnitude and direction of the final velocity. Again, we're just using these formulas here. You need to calculate the final velocity in the x and the final velocity in the y. So start with the one in the x. So you will say the final velocity in the x is given by VO cos theta. So the final velocity in the x is going to be, this will be 65 cos 37. So the final velocity in the x is going to be equals to, so you say 65 cos 37. So you're getting 51.9 meters per second. And then you also determine the final velocity in the y using this formula here. So you say the final velocity in the y is going to be given by VO sine theta. Then here you choose either plus or minus. So the motion is upward, so you get a minus GT. So meaning the final velocity in the y is going to be equals to 65 sine 37 minus 9.8 times the time of flight, which was 10.4. So the final velocity in the y is going to be equals to, so you can just punch 65 sine 37. We are getting 39.1 minus 9.8 multiplied by 10.4. We are getting 101.92. So meaning the final velocity in the y is going to be equals to 39.1. You are getting negative 62.8 meters per second. So now that you've calculated the final velocity in the x and the final velocity in the y, you can calculate the magnitude and the direction. So you can say the magnitude of the final velocity will be given by the square root of the final velocity in the x squared plus the final velocity in the y squared. So the magnitude will be given by the square root of 51.9 squared plus negative 62.8 squared. So the magnitude is going to be equals to, so 51.9 squared plus 62.8 squared, and the square root of that, we are going to get 81.5 meters per second. And then from there, the direction will be given by the tan inverse, the final velocity in the y divided by the final velocity in the x. So theta will be given by tan inverse. This will be negative 62.8 over 51.9. So theta is going to be equals to, this is 62.8 divided by 51.9. Then tan inverse, you are getting 50.4, of which the negative here just shows that the angle, this angle here is below the positive x-axis. Or if you want, you can get this to be the positives. You just get 62.8 divided by 51.2. And then you get 50.4. Then you locate the quadrant. You say, well, the final velocity in the y is in the negative region, so you plot the negative. Then the one for the velocity in the x, it's in the positive, so you plot the positive in between the two quadrants. So this will be your 50.4. Then you read it with respect to a positive x-axis, where now you will say the theta is going to be 360 minus 50.4. So meaning your theta is going to be equals to 309. So this will be 309.6. 6 degrees. This is with respect to a positive x-axis, or you can just leave your final answer here to say theta is 50.4 below the positive x-axis, or you say with respect to the positive x-axis, which is going to be 309. So this is how you answer a question when you're given a sketch like that. So if they asked you to calculate the maximum height, in this case, if they said maybe calculate the maximum height from the ground, you can apply this formula, which is, you can just go directly. So the formula for maximum height is this one here. Yeah, if they ask you to calculate the time taken to reach maximum height, you can also apply this one. So these are the only specific formulas that you have under this sketch. For all other calculations, you don't need to remember any formula. You just go back to the general ones which are given here. Okay, so this is just an example under oblique projectile motion. Then we'll do the rest of the examples in class. Okay.